In this video, we'll look through the notes for section 2.1, which is called the Cauchy problem for the heat equation. We start with an initial value problem on the real line. This initial value problem is for the heat equation, so we start with the partial derivative of u with respect to t is equal to some constant k times the second partial derivative of u with respect to x, the heat equation. This is for all x in R. In other words, there's no boundary here. So that means we don't expect any boundary conditions. We do have an initial condition that you see here. U at x comma 0 is equal to phi at x for all x in R. That is, we have an initial temperature at every x value. And this is given to us in terms of a function, which we're calling phi at x, but this is a prescribed function, a function which is given to us, so it's expected that we know what this function phi is. As I mentioned, there is no boundary here, so there are no boundary conditions, but we expect that there will be some conditions at infinity. Perhaps we want the function to be bounded, or maybe decaying as x goes off to infinity or minus infinity, something that in some sense is well behaved. A pure initial value problem like this, with no boundary conditions, is known as a Cauchy problem. This is a U here, C-A-U-C-H-Y. A Cauchy problem. We start with the special case where phi is a step function. So let's look at a related problem where our state variable is w. So w sub t equals k times w sub xx. Again, where x is in R and t is a positive number. And our initial condition on w is given by this piecewise defined function. So w at x comma 0 is equal to 0 if x is less than 0, and then it's equal to some value w sub 0 if x is greater than 0. So this is a step function. If we were to graph it, this is the x-axis and this is the w-axis, then the idea is it's going to be 0 until you get to this point, until you get to x equals 0, and then it's going to jump either up or down to w0. Now w0 could be negative, and of course then it's down here. But the idea is that it's a step function. So we use what's called the pi theorem. Whenever there is a physical law relating dimensioned quantities, q1 to qm, then there is an equivalent law relating the independent dimensionless quantities formed by q1 up to qm. So let's actually apply it in this case to see what we have in mind. So we know that w and w sub 0 both are measured in degrees, so w divided by w0 is dimensionless. So that means that we expect that we can relate this quantity, this ratio, w to w0, to some other relationship using the other variables. So if we look at the other variables here, we have x, which is measured in length, we have t, which is measured in time, and we have our constant k, which is length squared per time. So if you put all that together in this way, in this ratio, x to the square root of 4kt, this is a dimensionless quantity. Now here, the 4 is included for convenience. It's not strictly speaking necessary, but it will come up again later in a way that we'll be glad that it's there. So what we see here is that we have two dimensionless quantities that use up all of the variables. We have the ratio of w to w0, and then the other variables appear in this ratio, x to the square root of 4kt. Now, k isn't a variable, but it's a quantity. So what we're seeing here is that we've related all of the quantities. Or we haven't related them yet, but we found these independent, and by independent we mean that here we have a w and w0, and here we use the other letters, the other quantities, but we don't have any overlap. There's no w or w0 in this second quantity. So we have these two independent dimensionless quantities formed by w, w0, x, k, and t. So the pi theorem says to us that there should be some relationship between these two dimensionless quantities, which is in some sense equivalent to the law that we have governed by the heat equation. So we expect a relationship like this. So we expect that there's some function f which relates the two quantities to each other. Now we don't know anything about f at this time. We just expect that there should be some f that makes this relationship hold. So for simplicity's sake, we'll just choose w0 to be 1. So that reduces, so to speak, our relationship to a statement about w being equal to a function of this quantity inside the parentheses, x divided by the square root of 4kt. Now at some point we're just going to find it convenient to let z be equal to that quantity, x over the square root of 4kt. So what this is actually telling us is that we have a relationship between w and z. So we can write w as a function of z. We want this w to be a solution to our initial value problem, not the one we started with, but this reformulation that you see here. We want this w to be a solution to this initial value problem. So that means we want w sub t to be equal to k times w sub xx, and we want it to satisfy the initial condition. So w at x comma 0 is equal to 0 for x negative, and w0 if x is greater than 0. Of course, we picked w0 be equal to 1, so this is a 1 right there. Okay, so let's just compute our partial derivatives. Here we don't know what f is, at least not yet, so we have to use the chain rule, and we have this f prime here. So w is equal to f at some variable z, but let's leave it in terms of this x over the square root of 4kt, because we're looking for the derivative with respect to t and the derivative with respect to x, and of course the second derivative with respect to x. So for that reason, we're going to keep w in terms of f at x over the square root of 4kt. So I just want to rewrite that somewhere. Let me just change the color here. So we want w is equal to f at x over the square root. I'm just rewriting the same thing here. Now I want to compute the derivative of that with respect to t. So it's a composition, f at a function. So we're computing the derivative with respect to t, so it's the derivative of the outside, so f prime, times the derivative of the inside with respect to t, which you see here. And then we can simplify that, as we've done here. Now we can do the same thing for the derivative of w with respect to x. It's a little bit easier because the derivative of the inside is just 1 over the square root of 4kt. So that gives us this expression here. That's the first derivative with respect to x. If we compute the second derivative with respect to x, we just end up with an f double prime, and then we end up with another factor of 1 over the square root of 4kt, so we end up with a square there. So notice that this is the square of a square root, so you get rid of the radical. And that gives us our next derivative, our second partial derivative with respect to x. Now, the differential equation says that the partial derivative with respect to t is equal to k times the second partial derivative with respect to w. Well, we've just computed these quantities, so we have the partial derivative of w with respect to t right here. So that's this one right there. And this is equal to w sub xx, which is right here. So this one is right here. So there's this k right here appears right there. Now notice that we canceled that k with that k. There was a k in the numerator and k in the denominator, and those canceled. So what do we have now? If we multiply this 4t over to the other side, that's that 4t, then on the right hand side we just have f double prime, which is right there. Now on the left, you can simplify. Here's a 4, and here's a 1/2, so that just leaves you with a 2. There's a negative, of course, in front, right there. So that gives us a -2. We also have this t right here. Let's just change the color. So we have this t right here, and we have a radical with a t cubed underneath it. So you can take out a factor of t. The radical t squared gives you a t, and that will cancel with this t, and then you're just left with that 1t underneath there. So notice that what we're left with, of course, we have this -2, as we mentioned, but then we have an x over the square root of 4kt. Now this quantity is what we were calling z. And when I say we were calling it z, I called it z up here, right up there. So that is z. So we've got a z here, and we've got a z here, and we've got a z here. So what we end up with, letting z be equal, well, z be equal to, I just want to do this one. If we let z be equal to x divided by radical 4kt, then we end up with a differential equation that you can see right here. But notice, this is an ordinary differential equation. It's a derivative of f, and f is a function of one variable, z. So we have an f prime and we have an f double prime. So this is a second order ODE. Second order ODE, which means we know how to solve it. And that's what we do here. So we get it into the standard form, which just basically means we get everything onto one side. So that f double prime there is right here, and then you just add this term to the other side. So you add it, and then you have 2z f prime. Let me get rid of all these extra lines here. So that f double prime is right there, and then you add this to the other side to get that. So this is a second order ODE. Now, it's second order in F. So it's a second order ODE in F. However, it's a first order ODE in terms of F prime. Notice in this equation here, we now don't have, we have an f prime and an f double prime, but there is no f. So this is a first order ODE in terms of f prime. So if you want, let u be equal to f prime, then this differential equation that you see here becomes u prime plus 2zu equals 0. So you can see that this is a first order ordinary differential equation in terms of u. What that means is we can use an integrating factor. And in this case, the integrating factor is e to the z squared. It's e to the z squared because of that 2z there. So you have this 2z, so you need to multiply by something that it will be e to the something, and when you differentiate that something, you get 2z. So the integrating factor here, integrating factor is e to the z squared. And that's why we have it written out here like that. So this integrating factor allows us to write the left-hand side of this equation as a derivative, where we've used the product rule, or we've undone the product rule, so to speak. So if we differentiate this expression, this product, we see that it's the derivative of f prime, which is f double prime, times e to the z squared, and then it's plus the derivative of e to the z squared, which is this term right here. So this is the derivative of e to the z squared, times f prime. So writing it this way, we have that the derivative with respect to z of this expression is equal to 0. That means that that expression must be constant. So because we're differentiating this, remember, this is not a partial differential equation, this is an ordinary differential equation where our only independent variable is z. So if you differentiate this expression with respect to z, you get 0. That means it must be constant. So e to the z squared times f prime of z is some constant, which we're going to call c1 because later on there's going to be a c2. So we call it c1. Let's divide now by e to the z squared, and that's how we end up with this expression. So we have f prime of z is equal to some constant times e to the negative z squared, right here. Our goal is to find f, but we have the derivative, so we merely antidifferentiate. I say merely antidifferentiate, of course, the thing that you see here doesn't have an elementary antiderivative, so we use the fundamental theorem of calculus, and we write the antiderivative in terms of a definite integral. So that means that f is equal to c1 times the antiderivative of e to the minus z squared, which we're writing as a definite integral here. So e to the minus z squared, the antiderivative of that we have here using the fundamental theorem of calculus. But of course we need to add in a constant of integration, and that constant of integration is right here. So this is constant of integration, and that's we'll call C2, which is why we called the first constant C1. So now we have these two constants here. But importantly, we've identified f. We've identified what f is. Remember what f actually told us. If we just scroll back, when we introduced f, w was equal to f at z. And now we know what f is. So this is f. So that means w is equal to f of z. So here's w. It's equal to f of z. So w at x comma t is equal to f at z. Remember what z was. We have that up right here. Let's just change the color again. Let me just rewrite that. Z is equal, it's a little bit sloppy, let's try that. Z is equal to x over the square root of 4kt. So we just take that value for z and we plug it in right there. So that's this thing right there. So we have the upper limit of integration is z, but z is equal to x over the square root of 4kt. So what we've done is we've just rewritten it in terms of x and t. So this gives us our solution to the initial value problem. And when I say the initial value problem, I'm talking about this initial value problem here, where our initial condition was defined using a step function. It's this step function. Of course, we did it with the unit step function because we assumed that w sub 0 was equal to 1. We made that assumption right here, or rather right there. But we made that assumption, so that was the unit step function. So let's go back to where we're at here. Okay. So what can we say about this expression? We don't have any boundary conditions, but we do have an initial condition. And remember, it was in terms of that unit step function. So we know that w at x comma 0 is equal to 1 if x is greater than 0, and w at x comma 0 is equal to 0 if x is negative. So we're going to use that fact. So let's look at the case where x is positive. So we can actually write down what w at x comma 0 is. And it's equal to, this is our formula here. So x is some fixed positive number. So we have that w at x comma t is equal to c1 times the integral from 0 to x over the square root of 4kt e to the minus r squared dr. r plus c2. So we can't just plug in x at t equals 0 because we have a t in the denominator there, but we can compute the limit. So the initial condition says that the limit as t goes to 0 from the positive side, because t can't be negative because it represents time, wx comma t, this is going to equal w at x comma 0, which is w0, which is 1 in this case. So we know that if we compute this limit, it's going to be equal to 1. So here we've computed that limit. So if we compute the limit as t goes to 0 from the positive side, so x is some arbitrary but fixed positive number here. So we're computing this limit as t goes to 0 from the positive side, so we're going to end up with this quantity in the upper limit of integration being infinite. So this is actually an improper integral right there. So we know that this integral, if we compute this whole thing complete with the constants, we're supposed to end up with a 1. So this is equal to 1. It's equal to this one right here. So it's equal to w0. That's the right side. And on the left side, we have all of that. That's this thing right here. The limit as t approaches 0 from the positive side of w at x comma t. That's this value right there. As it happens, we can compute this integral though. Or that is to say, we know the value of that integral. This is the integral from 0 to infinity of e to the negative r squared dr. This is not something we'd be able to compute in closed form if it wasn't an improper integral, if we had some number there other than infinity. But since it's infinity, we actually do know the value of this thing. It's the square root of pi over 2. So we actually know what that value is. So that tells us that c1 times the square root of pi over 2 plus c2 is equal to 1. So what we've done is we've written that equation right here. So that's this equation that we've just established. c1 times the square root of pi divided by 2 plus c2 is equal to 1. We can do the same thing now for negative x. If x is negative, then we know that, again, it's going to be equal to w0. This is equal to w0, but now w0 is 0. So it's the same expression. We're looking at the limit as t goes to 0 plus wx comma t. This is going to be equal to w at x comma 0, but now we're looking at x negative, and if x is negative, then this expression here is 0. It's w sub 0, which is 0 in this case. So that's where this comes from. And again, we're looking at t going to 0 from the positive side, but let's look at what's in the upper limit of integration again, right here. Now t is going to 0 from the positive side, of course. So we're going to something which is infinite, but x is a negative number. So now it's a negative number divided by this factor here, which is going to 0 from the positive side. So that means our upper limit of integration is now negative infinity, which is fine. We just have to swap them, and that's going to give us a minus sign. But that's actually the other half of this integral, so to speak. So we end up with a minus square root of pi over 2. So this equation gives us this equation right here. c1 times the opposite of the square root of pi over 2 plus c2 equals 0. And we can solve this equation, or this system of equations, for c1 and c2, and we get that c1 is 1 over the square root of pi and c2 is 1/2. So if we plug those in, we get a formula for w, which we have right here. So this is the solution to our initial value problem, where our initial value is given in terms of the unit step function. So we just comment that this expression here, if we ignore the 1/2, that expression is the error function, or the ERF function. So it's 1/2 times the earth function, because the earth function has a 2 there. So this is 1/2 of that. So it's 1/2 of the error function evaluated at the upper limit of integration. So it's x over the square root of 4kt. So we can write this w x comma t as, if we factor out that 1/2, there's also that 1/2 there. So that's this 1/2. So maybe I'll just this 1/2 and that 1/2, you factor out that 1/2, and that's that 1/2. And then you just end up with the error function at this quantity, which we were calling z earlier, plus 1. So here we go. That's the error function at z. So we found this w, which satisfies our initial value problem. We now claim that the partial derivative of w with respect to x satisfies the heat equation. We know that w satisfies the heat equation, so we know that w sub t is equal to k times w sub xx. And we claim that the same equation holds if you replace w with the partial derivative of w with respect to x. This is actually fairly easy to show. You just differentiate both sides with respect to x, and what do you end up with? So you start with this equation, and then you differentiate both sides of that equation with respect to x. So on the left side, you just end up with the mixed partial, w with respect to t and x. On the right side, k is constant, so it just comes out, but then you're differentiating the second derivative with respect to x again, and so then you end up with the third derivative of w with respect to x. So the mixed partials, as long as we're assuming enough continuity here, the mixed partials are equal, so we can swap the order. So w sub tx becomes the same as w sub xt. So those are the same, assuming they're continuous. So what does that mean? This term, w sub xt, that's the partial of w with respect to x differentiated with respect to t. So that's what we have here. So first you differentiate with respect to x and then with respect to t. The triple derivative of w with respect to x is the same as first differentiating with respect to x and then computing the second derivative of that with respect to x. So what we end up with is wx, w sub x, the partial derivative of w with respect to x, satisfying the heat equation. So it's not hard to show, it's just keeping track of your derivatives. So this w sub x is an important function. So let's give it a name. Let's call it g. So g at xt is equal to the partial derivative of w with respect to x. We can actually compute it just using the fundamental theorem of calculus, and we're differentiating with respect to x this w. This is w here. This expression right here. This is w at x comma t, and we want to differentiate that with respect to x. And we just use the chain rule and the fundamental theorem of calculus, and this integrand pops out, so you end up with e to the minus r squared, but r is equal to x over the square root of 4kt, so that's where that comes from. But then you have to multiply by the derivative of what's inside, so you have to multiply by the derivative of that, which is this expression right here, 1 over the square root of 4kt. This is a constant, so when you differentiate that 1/2, it goes away. So in other words, if you simplify this, so here we have 1 over the square root of pi times 1 over the square root of 4kt, you just end up with 1 over the square root of 4 pi kt times this expression here. So it's e to the something. We had e to the minus k over the square root of 4kt quantity squared. So in the numerator you end up with an x squared. In the denominator the square cancels with the radical and you just end up with 4kt. So this is our function g. It's the partial derivative of w with respect to x. This is an important function, and so it has a name. Actually, it has several names. The function g is called the heat kernel, or the fundamental solution of the heat equation. It's also called the Green's function, which is why we call it g for green. Note that g is a probability density function. So for all t greater than 0, the integral, the doubly improper integral from minus infinity to infinity of g at xt of dx is equal to 1. This is an important property, which comes up again and again. So we know that g satisfies the heat equation, and indeed g at x minus y comma t also satisfies the heat equation with unit heat source at y. In this case, we're just translating, so that doesn't affect the fact that it satisfies the heat equation. So that satisfies the heat equation with unit heat source, which is what we've been looking at. So if you multiply that by phi at y, that will satisfy the heat equation with source at y having magnitude phi at y. Here we're imagining that y is a constant. Y is some picked constant. We don't know what it is. It's an arbitrary constant. But at some y, we translate, for some fixed y, we translate so everything is happening at that y. That's where the source is being applied. It's happening at y. And if it was a unit source, then we would just have g at x minus y comma t, because you're multiplying by 1 to get the right value. But if it's not a unit source, but a source having magnitude phi at y, then you multiply g at x minus y comma t by that magnitude phi at y. So this will satisfy the heat equation with source at y having magnitude phi at y. So by the superposition principle, we can then take linear combinations of these things. If we have a whole continuum, then we do that through integration. So u at x comma t equals the integral from minus infinity to infinity of phi y times g at x minus y comma t dy is a solution to the original Cauchy problem, as long as phi meets reasonable requirements, such as being bounded and continuous on R, which is usually a reasonable requirement to insist upon. So this gives us a solution to the Cauchy problem that we started with. If we start with the original problem, and let me just scroll back to the beginning so we can remind ourselves what the original problem was. So if we scroll back to the beginning, the original Cauchy problem for the heat equation is right here. So that's u sub t equals k times u sub xx, where the initial condition is given by this phi. We changed the problem and we were looking at a simple case, which is a case of a source which has magnitude w sub 0. And then we further assumed that w sub 0 was 1 so that we had a unit source. So our original problem had this initial condition phi at x. So now what we've done is we've gone through this first simplifying assumption where we had a step function, and then we found a solution for that problem, that initial value problem. And then what we comment on here is that we can translate to get a unit heat source at any y. And then we can multiply by the magnitude, which is our W0 essentially. But we're calling that phi at y because it depends on y. And the magnitude is given by this function phi. So phi at y. And then basically you add them all together. Now again, if you have a continuum, the way you add things together is by integrating. But what this gives you is a solution to the original problem, where phi was our initial condition. So this gives us a solution to the Cauchy problem, provided that phi meets our reasonable requirements, such as being bounded and continuous. So this gives us our theorem, a solution to the Cauchy problem for the heat equation with phi a bounded and continuous function on R is here. So g, as I mentioned, is also called the Green's function for the Cauchy problem, so that's why we call it g. So any of these names can be applied: the Green's function, the heat kernel, or the fundamental solution. But whatever you want to call g, it enabled us to find a solution to the Cauchy problem for the heat equation. This is the pure initial value problem for the heat equation on an unbounded domain, meaning all of the real line.